Hello, welcome to the Computer Vision Learning Track. I want to let you understand that, being in this track is really, really a great deal. And I want you to know that I'm going to be your course instructor for this track. I am Elisha Odumakinde, and I am a computer vision engineer. In this first video, we are going to be learning about introduction to computer vision, and we're going to be diving into what exactly is computer vision all about. What are the different scopes of computer vision? We're also going to be talking about the application of computer vision with respect to the real world environment, right? Healthcare, transportation, logistics, and so many other things. And finally, we're going to be talking about image processing technique in computer vision. I want you to just sit back and follow through every tutorial. Is going to be very hands-on, it's going to be very practical, and it's going to be very intuitive. And I hope you learn so much. Stay tuned.
All right, let's dive right deep into it. So, what is computer vision? Computer vision is an aspect of deep learning that deals with the interpretation, understanding, and analytic of visual data like images and videos. So, what do we mean by visual data? Visual data is simply images or videos because they are data that has to do with the visual view of what we can see or what we can perceive by looking at something visual. So, an image data is a frame of detailed information, of detailed visual information, while the video data is a moving frame of visual of images. That's the difference between an image and a video. So, with respect to videos, the image are moving at a particular frame per second. When we say computer vision is an aspect of deep learning, so it means there are other aspects of deep learning. And what we're trying to achieve with respect to computer vision is simply how do we interpret visual data? How do we understand visual data? And how do we analyze visual data? What are the different scopes in computer vision? We have image and video processing. We have feature extraction. We have augmented reality. We have face detection. We have 3D reconstruction. These are different scopes in computer vision. We also have object detection and tracking. We also have image and video segmentation. We have robotics and reinforcement learning. We have image and video classification. We have vision transformers. We have deep learning, and we have OCR. So I'm going to dive real deep into each of all this scope and talk a little bit about them. What do they really entail so that we can have an idea of what they are? So, first and foremost, image and video processing tech. Image and video processing. It's an aspect of computer vision that deals with how images are being processed or how they are being analyzed in order to extract valuable information. And one of the techniques that is very paramount with respect to image and video processing is grayscaling. Grayscaling is simply a one channel image processing, and it has been proven with respect to grayscaling that it makes image processing faster, easy to understand, and easy for object detection. When we load an image, images come in three channels: the R component, the G component, and the RGB, the green component and the B component. Okay, but when it comes to grayscaling, we're basically trying to deal with just one channel instead of three channels in order to process an image. When we get hands-on, I'm going to show you how you can grayscale an image for faster processing, easy understanding, and for object detection. That will be demonstrated. Another example of image and video processing technique is denoising. Denoising is a simple way of removing noise via matrix manipulation or via matrix um, interpolation to improve image quality and analytics. So if you have an image, you want to improve the quality and it contains a lot of noise, one of the techniques you want to apply when it comes to image and video processing is what we call denoising. Another technique that you would love to know with respect to image and video processing is filtering. So what exactly is filtering? Filtering is for image enhancement and information extraction. So if you're trying to process an image, you want to be able to enhance the image or you want to be able to extract a particular information from the image. One of the techniques that you must have in your toolbox is what we call filtering. All right. Another technique you want to be familiar with is rescaling and cropping. Rescaling and cropping basically implies you have an image that is of a very huge dimension and you want to be able to resize it to a particular dimension that is fit to be loaded into the model, processed, and information extracted in order to have some valuable information from that image. When it is so large, it makes processing difficult. So hence, the reason why you want to rescale the image to a much more convenient size. So you have to be very familiar with what we call rescaling. All this will be demonstrated as we advance in this class. We also have cropping. Cropping basically implies you take a particular portion of the image and then you crop out that section for processing, which is the area of interest. Area of interest, that's AOC. That's cropping. Another another technique you need to be familiar with is thresholding. Thresholding is one of the prominent technique for image and video processing that deals with converting a grayscale image to a binary image. Sometimes at a particular threshold. And when we say threshold, you're setting the pixel value, the pixel threshold to a particular value, such that values less than that threshold is resolved to zero, and values greater than that particular threshold is resolved to one, thereby making processing of the image quite intuitive, faster, and easy to comprehend for the model. We also have smoothing. So, how do you enhance an image, or how do you process an image that seems to be rough or is so pixelated? Smoothing is a technique that actually fixes noise within a particular image and fixes the problem of image pixelation. That is, when we say pixelation, we are talking about displaying images that such that individual pixels are visible, such that you can basically see almost all the pixels, right? So smoothing is one of the way that you can actually fix noise and pixelation. Segmentation is also another image and video processing technique that you should be familiar with. Segmentation deals with partitioning of images into discrete groups of pixels. So you have a particular image and you want to be able to uh, crop out certain objects from an image. One of the ways, and this is used prominently with respect to uh, object detection, whereby you are trying to detect different type of objects. So one of the ways by which you can actually identify an object is when that object, the pixel associated with that particular object, is segmented out. So segmentation is an image processing technique that can also help enhance an image processing analytics or comprehension. So what is feature extraction? So that's that with respect to image and video processing. So let's talk a little bit about feature extraction. Feature extraction happens to be an aspect of computer vision or deep learning that deals with feature detection and extrapolation. And a typical example is scanning edge detection is a technique for feature extraction. Now, one of the reasons why I would say feature extraction deals with feature detection and extrapolation is that if you look at the image by the right side, you basically see that you have a motorcycle fed through a feature extraction algorithm, and you are literally trying to extract every feature associated with that particular motorcycle. And how can you basically do that? You do that with techniques like carrier detection and also contour. These are different techniques which is associated with feature extraction in order to extract every detailed information with respect to an image. As you can see, with respect to the motorcycle, the the rear tire is extracted, the front tire is extracted, the rear wheel, the front wheel, the pedal, and every other detail that has to do with the motorcycle is all captured on the right after being passed through a feature extraction algorithm. So it's a very interesting field when it comes to computer vision. All right, you another technique that I would love to lay more emphasis on with respect to feature extraction is homography transform. In the coming video, I'll be talking more about some of this technique, how they can be implemented with respect to uh, an image and how you can apply them to actually extract information or extract detail from an image and then leverage those information be able to make actionable decision with respect to what the image is trying to communicate and properly analyze them. All right, so let's move on to the next scope that has to do with augmented and virtual reality. I'm sure you're familiar with what augmented reality is. That's AR, or what virtual reality is. All right, so in this area, what we're trying to do is that we're trying to model the outside world, or we're trying to interact with the outside world like it's so real. And some of the technique that is being applied in such area are object detection, object tracking. These are some of the things, some of the major building blocks in computer vision that makes that field so prominent today, or that particular scope so prominent today. With object detection, with your knowledge in object detection, with your knowledge in object tracking, and your which is in computer vision, it is very flexible for you to be able to build out an augmented system or a virtual reality kind of system, all with the aid of computer vision. Computer vision also has another scope called face that has to do with detection. Face detection is also a scope of computer vision, and it has been proven to be an efficient technology. That is, computer vision has been proven to be an efficient technology with respect to face detection. And it's due to its ability to recognize objects, detect them, and track them. With computer vision, you can detect the eye, the nose, the mouth, the hair, and estimate facial gestures with computer vision. Let's move on. We also have what we call 3D reconstruction. 3D reconstruction is also a very interesting field on its own, and it deals with how you can capture or reconstruct a 3D object from just image samples of the view from different sides. 3D reconstruction is a pretty advanced concept of computer vision that deals with estimating what an object would look like by providing few information of the feature, that is, the views of what the feature or what the object looks like, and thereby reconstructing it. This alone has a lot of research application, and this alone also has a lot of engineering, and it's more or less like a field on its own under computer vision. Another field or another scope that you should be aware of is object detection and tracking. This is the most talked about part of computer vision that deals with how computer vision algorithms are trained to detect an object effectively, track it continuously across frames via detection algorithms like YOLO, efficient depth, and some other interesting algorithms. For object detection, basically, as you can see in the GIF on the right side, basically deals with identifying objects within a particular frame or within a video, and then tracking those objects. This is one of the most fundamental building blocks with respect to computer vision. Image and video segmentation. This is a part of computer vision that deals with segmenting detected objects with similar feature by uniquely identifying them or classifying them from others. So in a particular image, for instance, you have a human in that particular image, right? So how would you want to segment the human from the dog in the image? The dog has certain features, the human has certain features. And as a result of pixelation and with the aid of image and video segmentation, it is easy for you to segment the dog from the human. As you can see in this GIF on the right, you can basically see that the first view up is the real world view, and the view below is the segmentation view. You could see that computer vision basically gave this self-driving car or this car the ability to be able to see things by segmenting things. So you could see the road segmented as the road. You could see the trees segmented as trees, thereby giving the autonomous car the ability to be able to identify when it is so close to a tree or where or if it's still on the road. Computer vision also has another interesting aspect, which is in robotics and reinforcement learning. This is an aspect of computer vision that deals with mechanical moving parts of a machine interacting with its environment via vision so as to detect objects, classify objects, and recognize the objects. So as you can see by the right, you could see that the robot pick up the object and then do what it does best on the object. That is, it is able to pick it from where it should be to where it should not be and then arrange it, which is the code that is folded. So that's an aspect of computer vision. Computer vision made this a reality for the robot. Computer vision is also applicable to image and video classification. So this is an aspect of computer vision that deals with how you separate objects into classes. As you can see, there are other cars that were passing. So hence, you need to be able to categorize or or separate the objects of the car from the road, right? You can see it's giving them different color, right? The tree from the road and the like. So those are different classes that needs to be catered for. So computer vision makes it very easy for us to identify trees different from the road, different from the car, different from the pedestrian, and so many other things that we are basically familiar with. And when we talk about vision transformers, it's an aspect of computer vision that deals with using transformers as its own modeling backbone as opposed to the usage of convolution. It's a field on its own, whereby you are not trying to build models. Basically, a field when a field of modeling, whereby you are not trying to build visual model with the usage of convolution. For now, uh, you are now using transformers as the backbone in order to build that particular model. This is another scope, which is deep learning. And basically, what we're talking about in this case is the usage of convolution as opposed to transformers. That's a field on its own, whereby you are literally building models using convolution, convolutional algorithms, as opposed to the usage of transformers. Computer vision also has a scope called optical character recognition. And this is the aspect of computer vision that deals with the identification of characters in an image or in a video. As you can see in the GIF by the right, basically see that the vision model was able to identify plate numbers not only just detect the object, it is the plate number, it was also able to extract the text. All right, so let's talk about the application of computer vision. How is computer vision applicable in retail? For instance, computer vision is applicable with respect to item identification and then human trafficking. As you can see in the video, in the GIF by the right, you basically see there are people moving, trying to buy or pick something from the store, right? With the aid of computer vision, we can identify them and track them. That's object detection. And with the aid of computer vision, you can also identify, you know, what people are buying and track what those people are buying. So that's the aspect of computer vision in retail. Computer vision is also applicable in transportation, and it's applicable with respect to traffic control and vehicle tracking or counts. So if you're trying to build a computer vision model whereby you want to be able to track particular vehicle, a particular vehicle of a particular color, or you want to be able to count the number of vehicles that comes into a particular location with the aid of computer vision, that is very, very possible. Computer vision is also applicable in medicine. With computer vision, you can solve breast cancer detection problem. You can solve eye defects, early stage detection. You can solve medical imaging problem. All right. So there are different, medical issues, medical problems. With the aid of computer vision, diagnosis is made faster, diagnosis becomes better, and diagnosis becomes um, quicker with accurate precision. With computer vision in medicine, it is very, very easy to detect early appearances of some disease in the body that the doctor might not have seen or might not have captured as early enough. Or with the aid of computer vision, there could be forecast, there could be proper diagnosis and faster inferencing with respect to what the medical condition of a patient could look like based on the reports of the medical. Computer vision is also applicable in robotics. For instance, cross-folding, industrial counting or mobility of items, or robotic prosthesis, right? Computer vision makes all these things very, very possible. So if you're trying to build a robot that you want to be able to pick something from one place to another, right? Definitely you would want to leverage on the usage of computer vision and of course robotics. Computer vision is also applicable in agriculture, whereby you are thinking about smart farming or you are thinking about smart monitoring of farm animals. For instance, you have chicken, right? Or you have goats clustered, packed um, inside their, store or location. So with computer vision, you can literally build a vision model that monitors, you know, their response to the environment, monitors, their movements, and so many other things, all with the help of vision. Computer vision is also applicable in surveillance, and this literally has to do with face identification or tracking. So you have faces that you want to be able to track or you want to be able to identify. Computer vision makes this very, very easy and possible. Or you want to be able to monitor a person or track a particular person. Computer vision makes all this relatively easy. Therefore, it is applicable in surveillance. Computer vision can also be applicable in autonomous vehicles. For instance, is applicable with vehicle road alignment due to its vision. It's applicable to object detection, detecting objects as the car is moving, speed control and estimation, traffic detection, and responses. So with the aid of computer vision, autonomous vehicle is a reality. If not for computer vision, probably we might not be having, you know, autonomous vehicles today. Computer vision is also applicable to sport analytics. With the aid of computer vision, you can do person detection, you can do field segmentation, you can do team classification, you can do color detection, and you can do keyword detection. All these things is possible with the aid of computer vision. Computer vision is also applicable in optical character recognition. That's the plate number detection, number detection, okay, and also letter detection, that is character detection on those plates or in a written document. You can have a lot of documents that you want to scan. So you can scan those documents and extract every text in that document. So let's dive right deep into the overview of image processing technique. So we've spoken about image processing technique, and one of the things I want us to do is to click on this notebook and see, follow through the examples right there, which I'll be doing right now. I'll be guiding you through it in order for us to be able to um, demonstrate some image processing technique.
So let's get right straight into some hands-on experience with respect to image processing in computer vision. This time around, we would be working with this particular dsn.png file, which is available in your data folder. So dsn.png. So but before we start working with this file, I would love to talk about libraries that you should be familiar with. Libraries. So libraries that you should be familiar libraries you should be familiar with are: number one, OpenCV. Number two is Matplotlib. Number three is Google Colab. All right, so to work with OpenCV, you have to do CV2, and then with this you're able to import OpenCV. With this, you're able to import Matplotlib. We don't need NumPy, and then with this you are able to import Google Colab. All right, so once you run this cell, you have all the libraries installed, imported. All right, so the first thing we want to do is let's figure out how to load in an image. So to load an image, you have to do this, but in this case, you are working with this particular image. Yeah, you're working with this particular image, and the directory has to be corrected. So in this case, it is /content/dsn.png. And once you run this, now one thing about this is that it loads the image as a BGR. So BGR means blue, green, and red. That's the three different channels of an image. So once you run this, you have image. Now, so the question is, how do we know that this is actually a BGR? Right? So when you do plt.imshow img, which is plt.imshow the image, it's going to display the image as a BGR. As you can see, this is a BGR. All right. I would also want to say, what's the difference? How do you know that this is actually or how does the image actually look like? So you can actually do CV_IMSHOW. CV_IMSHOW displays the image as an RGB. So let's run it and let's see what we have. So you can see the difference. This is actually what the image looks like, and this is the BGR form. So in this case, the image here is an RGB. It was arranged the red form of the image, the green, and the blue. All right, and then we have the BGR, which is blue, green, red. That was the way the image was arranged. So it was flipped. RGB, BGR. Okay, so the R was flipped to the blue, and the blue was flipped to the R, and that's why it's looking like this. So which means the arrangement of your image really matters. All right. So one extra thing I would love to pinpoint or that we can do that you need to be aware of with respect to image processing, which this is basically an intro. So I'm just trying to give you a clue to is image dimension. So image dimension simply is okay, what's the shape of the image, and you'd run it like this, or what's the dimension of the image. Though actually when you do image show here, it gave us an idea. This image has an height of 0 to 530 something, I guess, and from 0 to 1024. So when we look at the dimension of the image, it says this image is 534 in height and 1024 in width, and the channel is 3. All right. So um img.shape gives us those information or those clue with respect to that particular image. All right, so let's do some grayscaling, which is um some things that we talked about in the class early on. So to do grayscaling, this is how you grayscale an image. So this image is come on. So this image is a BGR. So to view the image as a grayscale, you have to do what we call BGR to gray. BGR to gray converts the image, which is the BGR loaded form of the image from OpenCV, into grayscale. So when you run this, you have this. So this is what the BGR of the image looks like. All right. So what about if I want to view this image as an RGB? Okay. So viewing the image as an RGB. Over time, with respect to our class, um, I'm going to be showing more clearer terms. I'm going to be talking more about, okay, RGB counterpart, BGR counterpart, and why we should work with, grayscaling. But I'm just trying to introduce, this is an introductory class, me just trying to introduce you to some of all these things, BGR, RGB, grayscaling, and the likes. All right. So how do we convert? So I'm going to use the same way I wrote this. So I'm going to do from BGR to RGB. Okay. So we have IMG, let's say RGB is equals to CV2 CVT color. Then you convert the BGR, this image, it means whatever you're converting it from BGR to RGB, and then you can display the image as an RGB. So this is the RGB form of the image. All right, so another thing I would love to talk about is HSV. HSV stands for hue, saturation, and viewing. So HSV. All right, so how do we view the image as an HSV? All right, so you can convert the image from a BGR to HSV. All right, so I'm going to talk more about HSV later, but I'm just introducing you to some of the basic processing. Just it's just an introduction, right? Let's just have an idea of what we are going to be doing as we step forward in the class. All right, so when you run this, don't forget this image is BGR to HSV. So you're able to see the HSV form of the image. All right. So there's one more thing I would love to, pinpoint before we wrap up this class or this session. I would love to talk about contrast of an image or the brightness control of an image. So to control an image contrast, the brightness and the contrast, we have what we call
convert scale ABS with OpenCV. You're passing the image as a BGR, and then you have two parameters, which is the alpha and the beta. So in this case, let's just something like this alpha, and let's do something like this beta. So alpha controls the contrast, and beta controls, let's say alpha is 2, or let's just say 0.5, which controls the contrast control, and then control, and then beta is the brightness control. So let's just assume alpha is 0.5, beta is 0. Don't be scared to make mistake. So in this case, I want you to try different values of alpha and different values of beta, right? And let's see what, okay, let's call this, let's say adjusted. So I don't be biased towards the use of this word contrast. Adjusted. So let's call this adjusted. So let's see, what do we have when this, all right. So when brightness is 0 and contrast is like, let's say 0.5, this is what we get. What if we increase contrast to like, let's say 2.0? Are we going to get something better? Okay. So that's one of the reasons why I want you to try it out. Okay. Depending on your major goal with respect to an image, right? So you might want to set some specific value of alpha. Maybe you have an image that you want to analyze and the brightness is too high and you want to bring it down, or the brightness is too low, you want to take it up a little bit. So these are some of the things that you can do on an image too. But I want you to try very, very large values. If you increase brightness, let's say 100. So what do we have? Don't be scared to try out values. Okay, so you could see the difference when you increase it from 0 to 100. All right, so depending on what you actually want, so let me just bring the brightness down to 5. Let's see, can we increase contrast to 50? What are we gonna get? So you could see the difference between when contrast is what was it? I think it was at 5 before. Let's put it at 5. So you could see it looks a little sharper, but once it's increased, it's looking a little off. So let me put it at 0 or something. So I want you to just try it out, try out different values, try out different values, try out different to just see how the image responds to some of these different values, contrast, brightness, and the likes. And I'm very, very certain it's going to make a lot of sense.
All right, I want to say congratulations to have watched this video this far with respect to the introduction to computer vision. I can basically say that now you have an understanding of what computer vision is all about, and I can basically say that you understand the different applications and use cases where you can apply computer vision to in solving real life problems. And I will also want to say that you've been able to understand the basic processing techniques with respect to images in computer vision. All right, I want you to know that there's going to be an assignment posted on Google Classroom, right? This assignment, everything is well detailed, right? Just run through the notebook, run through the instructions, very, very chronological. Just follow through the instructions and then submit your solution via Google Classroom. I look forward to seeing your solution. See you in the next class.